Modern artificial intelligence is often presented as a digital black box, a system containing hundreds of billions of parameters that somehow generates human-like reasoning. But if we peel back the layers of these massive architectures, we find that every modern model is built from a single rudimentary unit, the perceptron. To understand how it works, we have to look at the difference between traditional math and machine learning. In a standard equation, you have a known rule, like multiply by 2. You plug in your input, and the equation gives you the answer. In machine learning, we have the inputs and the desired answers, but we don't have the rule. The machine is essentially blind, trying to find a mathematical function that explains how the data it's seeing actually connects. This creates a unique engineering challenge. We have to build an engine that can take a guess at that hidden function, measure its own failure, and then physically adjust itself until it maps reality. This calculation is the engine's blueprint. To find an output, the neuron takes an input, multiplies it by a weight, and adds a value called the bias. This isn't just a random string of operations. It is the exact formula used to draw a straight line on a graph. In the world of AI, your prediction is literally a geometric line. This weight parameter acts as the slope. With a weight of 1.0, we get a steady 45-degree diagonal. As we increase that weight to 2.0, the slope steepens. The neuron is now predicting a much more aggressive relationship between the input and the output. If we use a negative weight, the slope flips. As the input increases, the predicted output drops. However, weight alone is limited. No matter how much we change the slope, the line is stuck. It is always pinned to the graph's origin at 0. To map real-world data, the line needs to move freely. This is why we add bias. The bias acts as a vertical offset. By changing this value to 2.0, we unpin the line from 0 and shift the entire function upward, allowing it to intersect with data points anywhere on the map. At this fundamental level, learning is the repetitive act of calibrating these two geometric knobs, weight and bias, until the resulting line aligns with the target data. When first initialized, parameters are random. The initial prediction line will almost certainly miss the data points. To fix this, a cost function calculates the vertical distance between the line and the data to determine exactly how wrong it is. The system's only goal is to reduce this measured error to 0. But the neuron cannot simply guess new numbers. It needs to know which knob to turn, and by how much. It solves this using the chain rule from calculus. This allows the neuron to trace the error backward, assigning specific mathematical blame to the weight and the bias for their part in the failure. Once the blame is assigned, the machine applies a learning rate, taking a tiny calculated fraction of that error and subtracting it from the parameters to nudge the line toward the data. This process of backpropagation forces the neuron down a mathematical gradient. It is a survival mechanism that systematically eliminates error through constant incremental updates. Each time the machine updates parameters, it completes an epoch. Over hundreds of cycles, the regression line ticks closer to the data. Eventually, weight finds the correct angle, and bias finds the correct height. The cost hits 0. The pattern is officially captured. By simply minimizing its own failure, this single geometric equation has successfully modeled a hidden relationship. Scaling this up is what creates the systems we use today. But a single stilt Latin cannot write a poem or identify an image. Modern AI chains billions of these units into layers. By passing results through activation functions, thresholds deciding if a neuron fires, the system models complex, nonlinear curves. This allows the math to move beyond straight lines and map the intricate patterns of human language. The intelligence we see in large models is the collective result of these same geometric updates, executed across a landscape of billions of simultaneous operations.